Okay. Good morning, everyone, or good afternoon, or good night, depending on which time you're watching this. This is the current workshop for PCB design I'm doing for the Banshee UAV robotics team with the collaboration between Cal Poly Pomona and Robotics. Today, we're basically going to go over the quick concepts on how to design a PCB from start to finish. If you have a circuit in mind, you can make a PCB out of it, and then basically you can have it in your hands as kind of like a nice little way of displaying a circuit without having all the jumbled wires in between. Basically, your breadboard jumper wires are replaced with little copper inserts inside this little board here you design. And it's really useful for replicating circuits in case you have something we want to use over and over again, like a voltage regulator, right? A voltage regulator can be used across multiple projects, or something like an Arduino breakup board. Those regular Arduinos you see are actually PCBs. The actual chip on the Arduino is what controls it. So today's in workshop, we're going to be designing a voltage regulator circuit, a really basic one that takes whatever voltage input you put inside of it and gives you 5 volts and 3.3 volts out of it. And let me go ahead and share my screen to begin this. So that's the goal of today, to take a voltage regulator circuit and turn it into a PCB. And this is usually one of the most basic ones, or basic examples of PCB design, because usually voltage regulators are pretty simple components, but they are actually very useful. And the two, let me go ahead and share my screen so you can see the notes I'm going to take. The input's going to be whatever voltage source, like a 9-volt battery, and the output is going to be a 5 volts and 3.3 volt outputs. These two voltages are really useful because 5 volt will give you enough voltage, the optimal voltage for an Arduino or something similar, maybe like a sensor or something else. And 3.3 volt is really useful for something like an RF module. So NRF 24L01s for wireless communication across a radio signal utilizes 3.3 volts. So in general, let's see here. So in general, PCB design comes in basically 7 steps from start to finish. The first step you have is the actual circuit design. The second step will be your bill of materials. So writing down all the components that you might need to build the schematic. The third part is the schematic. So everything between step 3 and 6 or 7 here is done in Altium or whatever PCB designer software you use. Everything up here is usually prep work, right? And so the last step is you ordering the PCB on a PCB fabrication company like JLC PCB. CB, say that. Okay, so the circuit that we want to build today is the voltage regulator circuit. So voltage regulator circuit. And I personally didn't do any prep work for this workshop. I'm just going to go and wing it all. But I'm going to show you that it's pretty simple if you get the initial circuit down. Circuit. So in the last circuits workshop, we went ahead and designed a voltage divider. And that took a little bit of circuit theory and a little bit of understanding like how circuits work. However, voltage regulators are much more simple than that. Circuit. So basically, if we drop a black box theory of what we want to build, our inputs will be something like 9 volts, right? And we want to take out a 5 volt rail, and we want to take out the 3.3 volt rail outside of it. The 5 volt rail can be used for things like Arduinos, motors, sensors, name it. 3.3 volts can be used for like low voltage BLE applications, so like Bluetooth. Can be used for radio frequency control, so like different types of wireless control, or if you just want like a low voltage for LED control, something like that too. So that's what our goal is. We're going to have this be our PCB. PCB is the black box. And we're just going to build the circuit really quick. So when you're building a voltage regulator, a lot of times you can either use a voltage divider to do so. You can use a series of transistors, or you can go ahead and just use a chip that's already made for you. Usually this is a common chip like the LM317. It looks like this. Let's say this is the LM317. You can also have another chip that looks very similar. This is the LM7805. And then this is the one that I'm going to be introducing you today, which is going to be the AMS1117 series. Now, these all do the same thing. They regulate voltage. They are all linear voltage regulators. So they take a voltage, a specified voltage from the beginning, like an input voltage, and then they clamp it down to a DC voltage at the end. Usually this is like 5 volts or 3.3 volts. For the example of LM317 and LM7805, these usually come with an adjustment pin. An adjustment pin you'll usually see on the data sheet as called ADJ. AMS117 comes in different variations. So this is the first regulator. The AMS117 can come in a 5-volt variant, a 3.3-volt variant, a 1.5-volt variant. I've seen like 2.7 volts before variants, and then it also has an adjustment variant. So inside of this little chip here, this little chip is going to be a SMD component actually. More commonly seen in the AMS117. SMD stands for surface mount device. These variants, all they do is say, okay, what is my output going to be? Is my output going to be 5 volts, 3.3 volts, 1.5 volts, 2.7 volts, or is it adjustable based on the center pin? So using this one chip, we can basically eliminate all the circuits. We don't even need to understand like much of circuit theory. We just need to understand that we can put in 9 volts and we can get out 5 volts or 3.3 volts. Using this one chip here. So what we're going to do is we are going to actually use the 5-volt variant and a 3.3-volt variant on our PCB in order to take in a input and spit out like an output, like a filtered output, using these 5 volts and 3.3 volts. So before I go ahead and build the circuit, I would just like to show you guys the data sheet for this. Now, the data sheet is really important. It's a really important piece of information that you always want to look at when doing any sort of circuit design or PCB design, because a lot of times you're going to use things like Arduinos, right? Those are data sheets. You're going to use like potentiometers, maybe like different chips, maybe like the ACS chip, which is for a Hall effect current sensor. You can have a joystick, which also has a data sheet, and like maybe an LED that also has a data sheet that tells you like what voltage it's gonna, what voltage drop it has across the LED. So in general, data sheets are really useful. They can tell you how much voltage the piece can take, how much current can go through it, and what safety measures you need to take. And also, the most importantly, they also have examples for you. So like this is the AMS117 bipolar linear voltage regulator, and you can see that it is a 1 amp. So at the most, you can pass 1 amp of current through it. Actually, it says here that the maximum output current is 1.4 amps, but just to be safe, it's 1 amp. Now, in case you want more current to come out of this linear regulator, you can like stack these in parallel, and which we have actually done in our project before. But if it comes to necessary in which you need like 2 to 3 amps, you can stack these in parallel. So in general, they already gave the circuit to us, right? The typical application here says, if I put a V in here and I just stick the chip in the middle, right? This chip has 3 terminals, a V in, a V out, and ground. I can take V out here, and V out will be my output voltage. And you see here, it says that usually AMS117 has a fixed version. The fixed version is 1.2, 1.8, 2.5, 2.85, 3.3 volts, and 5 volts, right? This is our fixed version, and it's what we want. So if we just use this chip, we know that we'll get 5 volts out, or we know we'll get 3.3 volts out. AMS117 also has an adjustable version, which can provide an output voltage from 1.25 to 12 volts with only 2 external resistors. These are usually your voltage divider. So in case you want to get more complicated as to what voltage you actually want, say you have a battery that only accepts 7.2 volts, you can use this adjustable version. But again, just keep in mind that the output current is 1 amp at the load. And if you want more, you can put these in parallel. All right, so we can see here on the typical application that there are 2 capacitors. The capacitor on the left is known as an electrolytic capacitor. Sorry, this is a ceramic capacitor because it is not polarized, right? The straight lines indicate that you can either flip the capacitor forwards or backwards and it won't make a difference. The one with the curved line is a polarized capacitor, usually an electrolytic capacitor. In general, it doesn't matter what capacitor you use, as long as you understand that an electrolytic capacitor, a capacitor or a polarized capacitor can only be connected in one direction. And usually they look something like this here. So electrolytic capacitors come in these like long cylindrical shapes. They usually have a plus side and a minus side. And if you overvolt them, it blows up and goes boom. And I'm sure Sander has has seen that before. Ceramic capacitors don't go boom. Usually they are like little tiny little things. My drawing's extremely bad, but they're usually smaller. They usually are a little, I wonder if I have some here I can show you. I've been sorting through my my stuff the other day, so I'm sure I have them. Oh, here it is. Okay. Yeah, so back when I did the workshop set at Hyperloop, I have like a bunch of capacitors in stock here. So these capacitors are really important because they're used to filter out noise. Noise is when you don't have like a straight DC voltage line, rather than something, some inductive or capacitive component inside the AMS1117 causes a little bit of like fibrillation inside the voltage. So like it's not straight, it's not completely straight, and it's like a ripple of like voltage going up and down that causes like discrepancies in your actual circuit. So in order to compensate for this, usually circuit designers will put these capacitors connecting from the VIN and ground and through VF from ground just to smoothen out the DC voltage, because these capacitors, if it detects a change in voltage, it will allow current to flow through it. Usually that's like the layman's description of what's going on there. Give me a second, I need to find my capacitors here. But in order to prevent, our circuit from malfunctioning, we usually put these capacitors here just to keep it safe. And let me see if I can find the example of the electrolytic and the capacitors for you. Oh, here it is. I have a bunch right here. So these are usually, all right, there you go. These are the ceramic capacitors. They're not polarized, non-polarized. You can connect them forward and backwards. They're usually pretty small. These are also through-hole components. So if you're designing a PCB for these, you need to make sure they go all the way through, right? And if I can find my other capacitors. I cannot. Oh, here they are. Here's some chunky capacitors. These were like ridiculously expensive. Just a side tangent. I bought these off UXL on Amazon, which you should never do. And these turned out to be really expensive capacitors, but I used them in my Blinky Learner soldering kits for Cal Poly Pomona. So you can see here that there is usually a cylindrical component on the top and then legs on the bottom. The plus side is usually the longer side, and the minus end is on the negative side. So when you're connecting this to a PCB, you got to be careful. Usually these capacitors have a voltage rating. So this one has a 250 volts rating. The higher it is, usually it's more expensive. So this thing can take over 250 volts before exploding. Now, if the capacitor is made really well, it won't actually explode. It'll just like fizz a little bit and let out some air at the top. But if it's a cheap Chinese made capacitor, then it'll go kaboom. Now, you can try this on yourself, but you gotta know, just you want to be safe, right? Some capacitors you can see have like maximum voltage rating of 10 volts. So if you connect like a 12-volt source to it, it'll explode. But the force that the capacitor explodes with is enough to tear straight through your hand. So just be careful. So what we see here is we want to replicate this circuit, the AMS117 circuit. We want to put some protection capacitors on each end to filter out noise. And I could just draw some noise for you. Let's say we have a V in, like an input voltage coming in like this. This is a DC voltage of 9 volts. Let's say this is voltage, this is time, this is 9 volts, right? Now, sometimes your input voltage will be attached to other parts of your circuit. And other parts of your circuit, if they have inductive or capacitive components, it will actually cause this line to look something like this. So it'll be 9 volts, but sometimes when something happens, you'll get something like this noise here. And now to smoothen out this noise, all we do is attach a capacitor from the source to ground. Because when something changes in the voltage, the capacitor will activate and allow current to flow through it. And it will keep the straight voltage going through into the AMS 117. Now, internally in the AMS 117, there are transistors and other components that cause an active change in voltage. So what we're going to get in the output is actually, let's say if this is a AMS 117, the 5-volt variance, we're going to get the 5-volt output at the end. So like voltage and time, and this is 5 volts, right? But again, we might get some noise in our output voltage. Maybe not like the biggest noise, but just some noise. And if we feed this noise into the rest of the circuit, we may get things like loss of packets. Maybe something like our bits got shifted at the end because of this like unusual occurrence, right? Let's say we want a 0 at the output, but since there's this noise here, our current sensor thinks it's a 1, and that causes us to have an error later on in the circuit. So to fix this, all we do is literally just add a capacitor. Usually this can be 10 microfarad. I also like 0.1 microfarad sometimes. Just the larger the capacitance, the longer time it'll take to hold that voltage in place. So I just want to go ahead and flatten it. And to flatten it, we use a capacitor. Okay, good. So first part of our circuit is solved. We know a way to get the voltage from like 9 volts to 5 volts using this one chip. And I didn't have to explain any circuit analysis or circuit theory. All right. So I'm going to go ahead and share my iPad screen again, and we're going to go back to designing the circuit. Now, I'm going to tell you it's a really simple circuit. All we need to do is use 2 of those AMS 117 chips. Okay, so the AMS 117, if we took a look at the data sheet, has 3 terminals. And I completely forgot to show you guys the actual terminal reading here, which I think is pretty interesting as well. So let's go ahead and go back to this diagram. And each data sheet for a circuit or for a chip will often come with 2 of these diagrams. One is the block diagram, which shows you the circuitry that is inside of the chip, right? You have your chip itself, and then you have some transistors and some resistors. You can see here there's a small little voltage divider at the end there. And the transistors is usually what causes the delay or the noise at the end. So you'll also see the pin configuration of an actual one of these IC packets. And you can see here we have a 1 pin, which is the VSS or adjustment pin. VSS is usually the voltage input. You have 2, which is the voltage output, and 3, which is the VIN. Actually, oh, hold on. Actually, this might be wrong. Usually, just kidding. Oh, wait, I was, sorry, I messed up there. VSS is the ground. So usually you have ground and then V out and then V in, and you'll be able to see this intermittently during the actual schematic. So VSS is ground. That was my bad. In the event that you have an adjustment, let's say adjustment version of the AMS 117, this pin 80J will also adjust the voltage given that you have 2 external resistors. And you can calculate them using the voltage divider algorithm in order to get your output voltage. So just know that 2 is the V out. That's probably the most important part, and 3 is V in. Now, if you want to build one of these circuits in real life, the AMS 117 unfortunately does not come with a through-hole breadboard design, but just know that this is true when you're building the circuit. And it's really hard to mess up because there's labels and everything. There is a 4th terminal. Usually it's the tab. So this little rectangle up here is called the tab. Right, this is the tab. And I'm telling you right now that the tab is usually connected straight to the VOUTs. If you go ahead and try to run a continuity test on a AMS 117 implementation on a board like an ESP8266, you'll find out that these 2 points are usually connected together. They're usually shorted together. If you like place your multimeter pins on each of the terminals, you'll hear a beep so that these 2 are connected together. This is important because when you're making the circuit, the Altium will actually ask you, oh, what do you want for the tab? And if you connect it to ground, it's wrong. And I've tested it before, and you usually get best results if you just connect it to V out. And it's better because you can take this and route it somewhere else too. Okay, now that we went over some of the restrictions, some of the circuitry, and some of the block diagrams for this AMS117 chip, let's go back to our notepad and actually draw the circuit this time. So share screen. Okay. Okay, so again, revisiting the block diagram, what we want to do is create a circuit that takes 9 volts as input and then outputs it as 5 volts and 3.3 volts, right? So which means we'll need AMS117, a 5 volt version and a 3.3 volt version, which is pretty simple. All we need to do is draw a block right here. Let's call this the AMS1117. I have my voltage input, I have my voltage output, and then I have ground. Just like the pins we saw on the data sheet, right? Let's call this the 5 volt version. So let's say I plug in a 9 volt battery into the VN. I'm just going to say, let's say I do a 9 volts inputs to the VN, and then I have outputs. I have, let's say 5 volts, right? And this can go straight to ground. Now, that's pretty much it for 9 volts to 5 volts. You have this chip in the middle, you have VN, you have your output, you have your ground. Okay, that's cool. But what about our filters? We need our filters, our capacitors, so that our outputs and inputs are both very stable. Stable DC voltage is what we want. So I'm going to go ahead and add some capacitors to the 9 volt input and the 5 volt output. I'm going to add a set of 2 capacitors. Actually, I found this to be the most stable version out of all my experiments. I usually like to have a 10 microfarad capacitor and a smaller capacitor to filter out the remaining noise coming out of 10 microfarad capacitor, so 0.1 microfarad. And then I'm going to mirror on the other side. So when the output comes out, I'm going to filter it using the big capacitor first, so like a 10 microfarad, and then filter it using a smaller capacitor, which is a 0.1 microfarad. That way, the outputs of the inputs and the outputs for this circuit will be nicely filtered, and I'll have a nice DC voltage at the end of all this. So to recap, basically, I have 9 volts coming in, 5 volts coming out. In case something happens with my DC voltage and causes some oscillations in between, I can use these capacitors to filter it out, right? So in case my voltage coming into the AMS117 looks like this, right? Some garbage. This capacitor will go ahead and filter it out and make it look like this. Maybe there's still some little bit of noise that we need to eliminate. And then we can move on to this capacitor, which takes this noise and eliminates it and turns it into a very nice straight line of 9 volts, right? And same going outwards. So let's say coming out of this AMS117 chip, we get 5 volts, but it's like very noisy 5 volts, right? And then at this capacitor, it'll filter it out into like a less noisy 5 volts. And then finally, after this capacitor, we'll have a very nice and straight line, which is 5 volts regulated, right? And so after all these capacitors are finished, we can have a circuit that regulates it from 9 volts DC to 5 volts DC. DC voltage is what we're caring about, which is great, right? So this is one part of our circuit done. We have a circuit that takes it from 9 volts and goes to 5 volts. But we also need a circuit that goes from 9 volts or whatever input and gives us 3.3 volts as an output, because we are going to need this for wireless communication, which is the more important part of this. So what I'm going to do is there are 2 ways to tackle this. You can either take 9 volts and clamp it down to 3.3 volts, or you can do what I'm going to do is I'm going to actually take the outputs of this 5 volt line, and I'm going to go ahead and actually copy the circuit right here. And I'm going to take the outputs of this line, which is 5 volts, and I'm going to drag it into the input of this second regulator here, which is going to be my 5 volts again. And then this time it's going to output 3.3 volts. Usually you can see 3.3 volts on Arduinos as like 3v3. That's because like usually decimals aren't very nice, but this is 3.3 volts. And I got to change my regulator to the 3.3 volt version too. Okay. So we've got our input circuit, we've got our output circuit, and they're connected in series, which means that we're going to get 9 volts output, and we can have a terminal output here that says 5 volts too. We're going to take the 5 volts and we're going to draw it into the next circuit. Okay, cool. This works. However, we have duplicate capacitors here. Now, we're all about being resourceful when we design a PCB. So if we have 2 sets of capacitors, one set on the top and one set on the bottom, that's kind of like redundant, right? We already filtered out most of the voltage. So all we got to do to conserve our capacitors is to delete the ones down below. So I'm just going to delete that, right? The things going into the 3.3 volt regulator is already filtered, right, by the previous circuit, which is why I didn't want to duplicate the circuit in the first place, right? This is good enough, right? We have filters on the beginning, intermittently, and at the end, which means we're going to have DC voltage, nice DC voltage all the way through, which is great. Okay, so we've designed our circuit now, and the next step to making a PCB is actually to put this into a bill of materials. So we want to determine how many of each component do we actually need. This is our second step. So we've done the circuit. Now we need to figure out bill of materials. Now, for larger circuits in which I'm going to provide for robotics once I get my spreadsheets working, usually you want to be really good at spreadsheets. And the reason is because it's a good way of organization. When you have large circuits, you need to figure out how much of each component you need, right? And the amount of components you need isn't even like going to be on the board. Sometimes it's you're going to need external ones, like for the 9 volt input, you're going to need a terminal block connector. And a terminal block connector is just one of these modules, which you see have like a screw top, and you can plug in like a 5 volt and a ground into it, and then it goes into the 9 volts, right? It's not usually shown in a circuit, but you need it because to physically build the circuit, you'll need some way of connecting your 9 volt battery, right? So 9 volt battery. Same for, let's say, the outputs. The outputs, 5 volts, you're also going to need a terminal block connector for that, right? You're going to need some way to access the output voltage, usually using a wire or something. Same for the 3.3 volt output. So right here, we're identifying some of the components that we're going to need. This is called a terminal block. And this is a 2-pin terminal block. I can actually show you what this looks like. I have a whole storage area of it right here. This is a 2-pin terminal block connector. Usually it looks like this. You can't put this on a breadboard nicely, but usually you can take like jumper wire and you can feed it into the holes. And then on the top here, you can screw it in to fasten it together, which makes for a really nice way of putting in power rather than trying to shove it into a breadboard. So terminal blocks are needed to access the actual voltage in case you want to screw in some wire, which is really useful in that. You have one for the 9 volts, you have one for the 5 volts, and you have one for the 3.3 volts. Now, is there anything else you need? Yes. And I'm going to say I would like, personally, for my PCBs, I always want to include an LED. And that's because if I plug something in, I want to see that my circuit is working, right? So I'm going to go ahead and take this 3.3 volt output, and then I'm going to feed this 3.3 volts. I'm going to feed this into an LED through a resistor of 330 ohms, and then into ground. Now, this might look a little weird because it's a disjointed circuit, but I'm going to go on and talk about something called reference nodes later on, and why that's useful for circuit design. So including to this circuit, I also know that I'm going to take my 3.3 volt node, which is just like an imaginary connection. I'm going to do this in a different color. This is an imaginary connection between this 3.3 volts and this 3.3 volts. Now, I'm using 3.3 volts instead of my 5 volt rail here because I know my 5 volt rail is probably going to put too much into the LED, and I don't really want that to happen. So I'm going to say, okay, I'm going to take 3.3 volts. I'm going to feed it into an LED, feed it into a resistor to control the current, and feed it into ground. And I usually call this the indicator LED. Okay, great. So bill of materials, what do we need? I'm going to put it over here. Bill of materials, usually you see this as BOM. I have I usually start with the bigger components. So my bigger components are going to be the AMS117. Let's see here. So the AMS117, one of them, AMS1117, and this is a 5-volt version. And I also have one of the AMS1117, the 3.3-volt version, right? How many capacitors do I have? Well, I have 1 10 microfarad, 2 10 microfarad, 3 10 microfarad. So 3, and I'm going to say 10 microfarad capacitors. And in this case, I'm actually going to use SMD components. Now, I know that I'm jumping through whole components, but I actually find that footprints for SMD components are usually easier to find. And if you design using SMD components, your PCB will be a lot smaller, and the PCB component company you order from will be much happier with you. So I'm going to say 10 microfarad and 1206 capacitors. So when you guys get into SMD capacitor design, you'll understand that the 1206 stands for the size, and usually these capacitors are extremely large, so they're really easy to solder together. However, they come with they're also very power intensive, so they can handle a lot of power through it. So usually you have other sizes like 0805, and then like I think it's 0604 or something like that. But usually the 1206 are the largest, and that's why I like using them, because they're good for beginners. So I'm also going to have 3 0.1 microfarad, and then I'm going to say 1206 capacitors. Now, if you want to go ahead and find a footprint, and a footprint is basically just like what this component looks like on the schematic, you're completely free to, right? And you can also use through-hole components as well. I would say just like I'm just doing this as for example, but it's the exact same if you want to find a variation of a different component. So we've got the capacitors, we've got the AMS chips. Now we need to get the terminal blocks. I can see here I have 1, 2, 3 terminal blocks. I'm going to have times 3 terminal block connectors, right? And this is 2-pin, okay? And then down here, I can't forget about my LEDs. So I'm going to say I'm going to have also times 1, 1206 LED. Let's say this is green, right? Doesn't really matter. It can be red if you want. Usually you find those big LED packs in stores anyways. And let's go ahead and add a resistor as well. So 1206 resistor. All right. So our bill of materials is complete. We have 1 AMS117 5-volt variation. We have 1 AMS117 3.3-volt variation. We have 3 10 microfarad capacitors. We have 3 0.1 microfarad capacitors. We have 3 terminal block connectors with 2 pins each. We have 1 1206 LED, which is green, and a 1206 resistor. By the way, just the 1206, know that it's an SMD component. Okay, so now we're done with the bill of materials. And now we can go ahead and boot up Altium and actually get into a schematic design. Okay, so I'm going to have this open so I can have it as a reference. And let's go ahead and open Altium now. All right, so I'm going to go ahead and boot this up. I'm going to start a new project. I'm going to call this Banshee demo. And I'm going to do a new schematic. It's like Banshee demo. Okay. Share screen. Okay, so when you open Altium, usually you won't see this. Usually you'll have to go to like File and New and Schematic, or a new project or something like the other. But once you get to this sheet, again, usually for PCB design, you have to go through a schematic, right? You have to put your circuit on this actual document, and then you can go into the PCB and actually start moving things around and routing it together. Okay, so I'm going to really quickly build what we want to design. We need a footprint for the AMS117, and we need some footprints for capacitors and resistors and whatnot. All right, so usually what you can do is you can go into this tool right here, which is the Altium Library Loader, which is created by the Sanexis people. If you don't have this, you can go ahead and Google it and download it. but this is an extension of Altium that allows you to grab footprints and symbols from like the billions of ECAD models out there. And it's actually really useful for that. So all you do to use this is you type in the name of the component. So here we have AMS1117, and we press enter, and the results will show right here. So we can see here that we have the AMS different versions of it. We can see here we have the 1.5 volt version, we have a 3.3 volt version, and we have a 5 volt version. Now we can see that it all looks pretty much the same, and I'm not going to complain about that. It looks pretty much the same. So if the different versions of AMS all have the same size, which means it has the same footprint. The footprint is the diagram on the PCB that shows you like where to put it and like what shape it is and where all the terminal blocks are and where all the pads are. So I'm going to go ahead and add this to my design. And you can see how in the background it actually draws out the parts. And it says, please check the bottom left corner to drag it into your schematic. So I have it right here. We can see that we have ground, V out and V in, all the same as before. And I'm actually going to take this, I'm going to double it because I already know that these are the same sizes. So 3.3 volts. They're the same size, so I can just use it the same way. Now, we have two of the AMS117 chips already, so we're already half done. Next, I need to find the capacitors. Now, unfortunately, this is a little bit difficult to do because if you search up, like, let's say 1206, which is the SMD size on here, let's see 1206. You'll find out that you have this piece, which is actually a resistor. If you scroll to the right here, you can see that this is the MCMR piece, which is a resistor. You have an LED. Oops. So this piece is a surface mount device resistor, and you have an LED down below, a fuse, and then you have more resistors. And you might be able to find a capacitor here, but it'll take a good while. So what you do is you actually go to some website like Mouser Electronics. Right here. And let's say you want to find a piece, right? If you want to find any electronic component, Mouser will usually have it. So let's say I want a capacitor. I already have a bunch of searches here. So let's say capacitor, SMD, and 1206. Not 1205, 1206. 1206. And I think this is the part I originally chose. Usually this one is a good one for 1206. And if you just buy any like standard 1206 resistor on the market, this will be the same footprint. It's really expensive. It's like 53 cents per capacitor, which is like insane. But what we're after here is the actual footprint of it. Now, it says there's no footprint currently available, but you can probably scroll down and find like another one. As long as it's 1206 size, it will probably suffice on your board. Now, I already have this in another project, so I'm just going to go ahead and grab it from it. So this piece right here is what I'm looking after. This one says it's a ceramic capacitor, and it's the size of 1206. So by that logic, I'm going to go ahead and use it. It says this footprint is missing. Why is it missing? Well, that shouldn't happen. It's missing because I don't have the CAD model on it. So let's see. I have to save this inside projects, Benchy demo, and then vreg. I have to import the library of the capacitor that I downloaded. So in order to do that, let's say you download a footprint off the internet of some part that you want to put into your PCB. All you got to do is press these three lines here, go to File-Based Library Preferences, and then go ahead and doesn't let me add. Let's say, why doesn't it let me add libraries? File-based library preferences. Nope. File-based library search. Give me a moment. Okay. So I have this here, the C1206 part. This is actually the capacitor component that worked for me. So it seems like I already have it right here, which is the one I want. So once you import the library package, which is this capacitor right here, you can actually go to the schematic library, which shows you the schematic here. And then you go to panels, SCH library, and then you go down here to place, and usually you can place it right down. I think that's how you do it. And then if it doesn't, it says it has no footprint, all you got to do is go to add footprint, and then you gotta find it inside your libraries. It's not showing it for me though. Stalled. Okay. Let's see if I can just like install it right now. All right. Yeah, that looks like the correct footprints. Let me go ahead and add that. And then it should give me the actual footprint of this. Okay. Okay. I don't know why it's doing that. It's weird. Footprint is missing. Oh, come on. All right, we'll deal with that later. But as of right now, I'm going to go ahead and get rid of this value. So I'm going to say the value is, let's say 10 microfarad. It must have been when I refreshed my Altium license yesterday. All my packages went missing. Okay, so we need 10 microfarad capacitors and then 10 capacitors that are 0.1. 0.1 microfarad. Okay. In this case, we'll also need another component. We need the terminal blocks next. So terminal block connectors 2-pin. Lucky for me, I already have this component right here. This component has worked for me in the past. Usually this is the terminal block connector. This one is the 282A36, and I believe it's on the library loader as well. And you can also find it on Mouser Electronics. So 282A36-2. I go ahead and find this. Yep, T connectivity, this terminal block connector, you just pop this into your design and get it loaded. So we need 3 of these things. And so I'm going to drag 3 of them here. Okay. Now we need a 1206 LED and 1206 resistor. So I already have this, but if you go ahead and search the 1206 component on the Altium library loader, you'll find it the same way. So in this case, I'm just going to drag this circuit straight into my design. If you do a lot of PCB design, you can actually use the same components over and over again, and it'll usually work out. So now we just need to draw our circuit, and we'll draw it exactly the same way it looks on our circuit that we designed. So we have a 10 microfarad capacitor here, and then a 0.1 farad, 0.1, oh, come on, 0.1 farad capacitor going into the AMS 5.0. And then coming out of it, we have a 10 microfarad capacitor right here. And then a 0.1 microfarad capacitor coming out of it right here. Okay, and this will feed itself into the AMS 1113 module right here. And then we'll have the final capacitors on the output side. So I'm holding it like this, and I'm pressing space to rotate. And that's a little hotkey that you can use to manage your components pretty well. And at the input, I'm going to put my 9-volt source, and I'm going to put a ground. And in the middle here, I'm also going to put one of these connectors. And then at the output, I'm going to put this connector here. Now, there is a standard for these connectors on which you should put as your power and ground. I believe usually 1 is your plus side and 2 is your minus side. So let me just make sure that that is true for this. 1 is your plus side and 2 is your minus side. So this is wrong. So I'm going to press X to flip it horizontally and then get it to be in the correct orientation like this. Okay. So this terminal block connector is going to be my 9 volts, so VN. This is going to be my 5-volt regulated, so 5-volt regulated. And this terminal block connector is going to be my 3V3 regulated. Okay, so now we need to wire everything up. And of course, I can't forget about this component, but I'll come back to that later when I talk about reference nodes. So in order to wire it together, all you need to do is you press Control W, and that creates a wire. Now this is our V in, so I'm going to wire this straight to V in. These capacitors will also go on this line. And I can't forget about ground. Usually in Altium, you can just like press the ground component and it'll create a ground net for you. Things are organized in Altium as nets or yeah, just nets. So when you're routing it, you can see that things are referenced to each other via nets. And I'll put a ground wire all the way down here because I know all of these are connected to ground. Now, schematic ordering or schematic, making your schematic look nice is very important. So you don't want wires crossing each other a lot because it makes it hard to read, which is why you have things like reference nodes. And I'll cover that in a bit. So if I go here and set this to ground. All right. Now I did say that the tab or EP is connected to Vout because that's what is going to be the output. So 9 volts goes in and then 5 volts will go out. So instead of wrapping this around here like this, which is cool, but it's also really hard to read, I'm going to go ahead and use a net label. Now, net labels are kind of like portals, right? It takes a wire and it transfers it from like this area into the next area. So if I go ahead and say net label 47, I'm going to change this to 5 volts out like that. And then I copy this and paste it to the output here on the tab. This is going to be the same wire as this line right here. So it's basically saying Vout is connected to the pin 4 here, EP like this, but without the very long wire. So this is really useful in case you want to make your circuits a lot neater and easier to read. Because again, communication is really important. And you want to make sure people can actually read your circuit and not get confused. So I'm going to put this to VN again. And again, the same thing. The Vout is going to be coming out through here. But this time, the Vout is 3.3 volts, right? So I'm going to say 3V3 out. Again, usually I put 3V3 because the decimals are hard to read. So I'm going to go ahead and put 3V3 out here. And now at my 3V3 regulator, I'm going to say this is going to go to plus and then 2 is going to go to minus as ground. And now whatever I connect to my 3V3 regulator is going to have 3 volts. Whatever I connect into the voltage in port is going to have voltage in. Now I left out my terminal block here, which has the 5-volt regulator, but that's okay. I don't want to try to stuff this terminal block inside the middle of the circuit because that'll be really confusing to read. So all I need to do is I connect the 2 to ground, and then I connect the 1 to my 5-volt output. And by doing this, I've basically connected a terminal block to this component right here. So instead of using wires, I use these cool little portals. Portals for wires, I like to call them. And just like same thing for this component here, right? I want to have a 3V3 line going into the diode or into the LED, and I want this output to be ground. So all I need to do is put ground here and then put 3V3 out here, and then boom, I am now complete. I have now completed the circuit, right? Pretty simple. I have 3 main circuits here in which I can actually label it using the text. And I'm just going to copy this text here, which I use for another circuit. And I'm going to say this is my linear voltage regulator, right? And let's say this is my indication LED. Okay. And let's say this is my 5 volts terminal block components, PCB components. Okay, so I basically have 3 main components in my schematic right here, which is great, right? And you know, if you want to be more professional, you can actually like put this here, 5 volts and 3 linear voltage regulator. Put your name and stuff. This I'm not going to release it to the public or anything, so this is fine. Okay, so once you have all your components down, now here's the moment of truth. You need to make this into a PCB. So I'm going to go ahead and go to new and create a PCB in here. And here is where you put all your components down, right? All your components down, you can like wire it and everything and make everything look very small and neat. This is kind of like the scary part, because now you design your circuit. You're hoping that all your footprints are correct and all your footprints are linked together. Usually that's not the case, but we can hope. So I'm going to name this vreg PCB doc. This is where you put down and arrange all your components. That's the bottom line here. So to do this, I'm going to go ahead and save my schematic. I'm going to go to design, I believe. Oh no. It does not have. Oh, it's in free documents. Oh, that's why. Oh no. Oh no. Oh no. It's actually not in the project. Okay, this brings up an important point. Whenever you're doing something along the lines of PCB design, make sure your documents are actually in the project, and not floating around in like blank areas. So I need to make sure my project is actually in Banshee demo.project PCB. That way, my schematic will actually be able to update the PCB document here. And it's yelling at me that errors have occurred because it can't find the capacitor footprint, which I was scared of, which means that I need to go back and try to add it to the library. So that's why it didn't let me add it to the library earlier, because the file wasn't actually inside of the stupid project, which was an oversight. Okay, now it lets me add the library, and because I have added the library, now it can find the actual footprint, I hope. So if I go to add, I go to footprint, and I go to browse, and I select this thing. If I press OK, will it actually let me load the footprint? Please. Footprint is missing. Huh. Yeah, so if I go ahead and wait, it found this one. Hold up. It found the footprint of this. Okay, I'll find what happened there. I'm gonna go ahead and annotate my schematics quietly, just because I'll make things easier on myself. Okay, I'm gonna go back to my PCB document, which has nothing in it. Great. We'll try updating it again. If I execute my changes, it goes to update the PCB document. You can see here that basically what I have here is all my components that are in my voltage regulator. I have my actual terminal blocks, which are very large. I have my AMS components right here. And I have my singular capacitor, a resistor, and the LED. So I think it actually worked. I just need to update the rest of them. So C1, I need to go ahead and add the footprints, and the footprint being this library here. Press OK. I don't know why it's not actually verifying that that is true, but beats me. And I'm going to do the same thing really quick for the rest of the capacitors. Okay, and then add the footprints. And the final one. Add the footprints. Oh, add footprints, browse this thing. Yes, yes. Okay, now I'm going to go ahead and update this. Hopefully they're all updated. Oh boy. Okay, good. Okay, all the footprints are in now. And we can start talking about how to organize everything on top of your window here. So you basically want to try to build your PCB how it looks like on the schematic or on the circuit. I'm going to go ahead and switch to 50 mil, which is the spacing between each of the components here. Now, mil stands for, I think it's like thousandths of an inch, or like, yeah, it's a thousandth of an inch. So 1,000 mil would be 1 inch. And that's the way they have imperial units on PCB design. It's a little bit weird like that. So I'm going to go ahead and plot my 5 volt regulator on the top corner here. If I press 3, I can actually see the 3D model for each of these. I can see that that's in the right direction. Usually the circle's on the back. And this is what my PCB looks like from the top-down view. So this looks great. I'm going to go ahead and place down each of my components now. Again, usually you want to be really neat on this. And let's say I have my VIN coming in, and then I have my 3 volt 3 regulator going out. So I'm going to put this right here. And my 5 volt regulator, I'm going to put this like in the middle. Okay. Just before I go on, I'm actually going to move the origin back up to the top corner there. So if I go to File, I go to, not File, it's Edit, Origin, Sets, and I'm going to put it to the top right corner. The reason I'm doing this is because usually you can see on the top left corner there, there's a top layer thing, and it shows like what position I'm in. This is useful in case you want to make it look really nice and like evenly space everything out and everything. But sometimes you don't have the time for that. So I'm going to go ahead and go straight to putting the AMS chips on. So this IC here is IC1, but in the document, it is the AMS 5.0. I'm going to rename this AMS 117-5 volts. I'm going to rename this AMS 1117-3.3. Just so that if I go ahead and go back to if I update the PCB schematic here, I can see that it updates the labels for me. All right. So I'm going to go ahead and position these normally. Now, I know that my capacitors must go between the VIN and the AMS. And you see how I can use this space mechanism to rotate these capacitors so that the net label, right, these little lines are connecting the VIN between these capacitors to the AMS 117. I want to try to unscramble this as much as possible, just because when I'm trying to draw a wire between the VIN port and the capacitors, it's going to look very, very neat and very organized. So now in general, based on some PCB theory, you always want your capacitors as close to each other as possible. This is just because if you have longer wires, you'll have greater resistances, and greater resistances account for greater error, which we don't really like to have. So I'm going to go ahead and position this like right here. Okay, now there is a cross here, but I'm not concerned about it because I'm going to eventually put a ground polygon port across this whole PCB, which means that every single ground connection will be connected to each other, right? A polygon port is just a copper layer that covers the entire front of the PCB for you, which is really useful in a lot of situations. So I'm going to put the 5 volt regulator in the middle right here. And then I'm going to put my, I need some filtration capacitors, I forgot. This will go right here and right here. Okay. And I'm going to go ahead and position this right here. I'm actually going to flip this. Yes, flip this. Just continue. And the reason I'm flipping this is because actually, nah, I'm going to ignore what I just said. This is fine. So after the 5 volt regulation, this goes straight into the AMS 117, which has a 5 volt, 3.3 volt out. And I'm going to put my remaining capacitors on the outside of this. Again, I'm going to position it so that my 3.3 volt output is on the top. And then I'm going to end it off with my terminal block on the other side. So just like gauging the total scope of things to make sure it looks decent, you know, it looks right. It looks pretty good. I think this could just use a little bit more spacing. Yeah, this looks all centered on top there. I'm not sure why. Okay, so I'm going to go ahead and just put this resistor here. We need a resistor and we need the LED. So I'm just going to put it like right about here. Okay, and that will pretty much, you know, make our PCB here. We have a VIN, we have capacitors, we have the AMS 117, we have 2 more capacitors here. We have the terminal block to access the 5 volts, and then we have a terminal block to access the 3.3 volts. And yeah, let me just line that up a little bit better. You'll notice that when I'm making this PCB, I'll actually have some square pads and some circular pads. In this case, I'm going to say that my default square pad is a VCC pad, which means that there's going to be 5 volts or a plus symbol at that square. But sometimes you'll have something different, like you want to have all grounds on square pads and stuff like that. It's just what kind of orientation or kind of standard you want to put on your PCB. And whatever you choose, that is completely fine. However, you just want to make sure your target audience or whoever's going to be using your PCB knows that. So in addition to putting like the square pads, you also want to put text signifying like the plus or minus symbol within your PCB. A good example of this is actually, yeah, well, okay, this one's a good example because look, I labeled all my pins so you know what you're going to put in this PCB. This is an Arduino Pro Micro breakout board that has both I2C and the RF controllers. And you'll see that I use the AMS117 here with a 3.3 volt line to feed it into an RF wireless communication module. And I already have labeled all the rest. It was a pain to get everything centered, but this is just an example of labeling your PCBs. Another example is this one, which is the Blinky Learner PCB that we have soldered together in one of the Hyperloop workshops. You'll see that I've upgraded a little bit, and I've also added like indications, like with plus and minus symbols, because people kept messing those up. And putting the LED symbol right here to indicate that, oh, the longer leg is the plus side and the shorter leg is the minus side, and stuff like this is really useful because you want your user to be able to assemble what you made on the PCB without having to like search through like documentation and like having to ask you on DMs and stuff like that. So what we have here is completely fine. The next step is actually to draw out the board itself. So if we go to the 3D view, we'll actually see that this looks fine, right? We have some components here, we have some chips here, we have our terminal blocks, and everything looks okay. Well, we might have to change some of the text of the labels later, but right now, if we just went ahead and ordered this PCB, we'll basically get this small area plus this huge like unused surface. So we need to like kind of like cut the PCB out inside the software first in order to do this. So I'm going to leave it a little bit of slack because I like to put mounting holes on my PCBs. And I'm going to start drawing lines around my PCB here. So I'm going to say, okay, I'm going to do this. I'm going to do this. You can draw just like loose lines. That's what I usually do around your PCB. Okay, so nothing is centered yet. This is just like a loose, approximation of where everything should go. You can center it later. And usually you do want to center this because it'll make it look a lot nicer. Now, there's a tool inside of Altium that you can use. I believe it exists in KiCad as well. If you do Control M, this is a measuring tool, and you can measure between like the pins and the outer edge. So this is 350 mils or 350 thousandths of an inch away from the edge of the PCB. And so I kind of want to make sure that is consistent with the other side. Looks like the other side is actually not as consistent horizontally. So I'm going to move this a little bit down. I think that'll fix it. Yeah. And it seems like this side is not consistent with the 3v3 out too, because 3v3 is at the bottom. So I'm going to flip this horizontally in the Y direction so that this is the case. Actually, no, I'm not going to touch that because it changes the orientation of the 3D area behind it as well. So you kind of want to do things to make sure that everything is even on both sides. So I see 400 mils here. So I'm going to drag this area. So this will be 350 mils. And then I'm going to drag it again. So this is going to be 300 and 250. Usually you want these terminal blocks to be as close to the edge as possible. So in this case, if this is 250 away, then I'm going to go ahead and drag everything here and then just decrease that edge a little bit. I think I need one more across this edge. Let me just go ahead and drag it one more and one more. Okay, so then if I go ahead and measure this again, I'll get 250 mils on this side, and I'll get 250 mils on this side. And that works out. Okay, so now we got to take care of the vertical edge. Again, you want the terminal blocks to be as close to the PCB edge as possible. So now I'm going to go ahead and move this all the way up here. And I'm going to go ahead and place the resistors and the LED down here. So it's a little more concentric with the PCB design. And then I can go ahead and move the bottom edge upwards. I think up to here would be okay. Now, the reason I'm leaving a bit of slack is because I still want to put my mounting holes there. Mounting holes are important in PCB design, actually, in case you want to take things a bit further with your PCB. So if you want to mount it to, like, let's say a 3D model and you don't want to use super glue, you can think ahead in advance and put mounting holes. And now there is a specific strategy to putting mounting holes. So I'll go ahead and first draw out some curved edges and then use those curved edges to space it out and draw the holes in. So in this case, I'm going to go ahead and actually make the board cutout just to show you how to do that. So to make the board cutout, you go ahead and press Shift and highlight all 4 lines, and then go ahead and find the board cutout tool. I always forgot where it is. Okay, so it's in design. You go to board shape. You define board shape from selected objects. This is why. This is why. So you gotta make sure that you don't have any slanted edges like this. Okay, let me go ahead and fix that real quick. This is really annoying. Oh no. Okay, let me just delete this, and then you just gotta lengthen it this way, lengthen it this way. Where'd it go? Extrude it this way. Wait, what happened? Where did my line go? Uh-oh. Okay, fix this. So we gotta have line here. Oh, I'm not in the right layer. Let me go to the top layer. Here. We gotta delete this little slant and move this downwards. Delete this little slant, move this upwards, and then move this to the right. Okay. Everything should be connected now so that I can highlight each of the 4 corners again. And board shape, define board shape. Okay, good. All right. So now I have the board shape complete. If I go ahead and look at the 3D view again, I can see that only this board shape remains, which is all my components plus the terminal block connectors, right? So that's pretty much it for board shape design. I'm going to improve on this now by adding a little bit of curves on the corner, like you see with the other PCBs. You can see on the Blinky Lunar PCB, I have curved edges and also some holes in here. So you can mount it to like a 3D model, which is, pretty cool. If you know how to do this and you know how to do CAD, which we'll talk about later today, it's really useful because you can do a lot with it. Okay, so I need to make sure that the top and the bottom are actually equidistant. So this is 400 mils and this is 350 mils. I screwed up there. All right, I'm gonna bring this a little bit downwards and that screwed up the entire, right, okay. Just make sure this doesn't happen again. Which it will. Okay. Give me a line. And I will say, in general, PCB design is a really lengthy process. Pays a lot, by the way. But it's a really lengthy process because if you have like more complicated designs, then you'll have to go back and look at the design a lot. It's a lot of trial and error in general that you have to go through. And usually you can't rush through it like an hour and a half like I'm doing right now. It's a very intensive process. And most of the intensive process is just looking at the PCB again and again to make sure that you don't screw it up. Oh, did I screw it up? Okay. Looks like it's open. So, oh goodness. Oh no. I don't know why the edges are bending like this. What's wrong with it? Okay. It looks fine. No, that doesn't look fine. I've never had this happen to me before, for board edges at least. Okay, let's try this again. Tools, design, board shape, define board shape. All right, that should be okay. Now, if I go ahead and probe the edges, that's 400 mils, and that's 400 mils again. Good. Okay. Now I'm going to go ahead and make 4 lines extruding from the top 4 corners. I'm going to check the top left corner where it says top layer, and then I'm going to make these lines 200 and 200 mils downward. I believe it's 200 mils downward. I think it is. Yeah. So 200 mils downwards. Same for this edge. So 200 mils upward. And this is how I'm going to build my corners. I'm going to build my 4 corners here. 200 mils downwards. Come on. 200 mils. And this step is purely to make it look prettier. Now I'm going to go ahead and make a circle at the end of each of these corners, which are going to be 50 mils across. Actually, this looks like a little bit too close to the VN. You do have to realize that this circle is made for a M2.5 by 6 millimeter screw. And the M2.5 by 6 millimeter screw has a head size of about 200 mils in diameter. So in this case, if you were to try to screw this onto this little circle right here, you would actually have to account for this size. And you can see the overlap, right? So if you try to screw something into this hole, it'll overlap with a VN block and you'll get some errors. So in this case, I'm actually going to take a step back. And instead of having it go with 200, 200, I'm going to go 150, 150. Okay. Like this. And that way it'll give it a little bit more room to drill a hole in so that we can screw something into this little board here. So full circle, 50 mils. This is the size of an M2.5 by 6 millimeter screw. So you're going to CAD something based on this board, to hold it together. You can do that. And actually, for the next workshop, I know I'm going way over time here. It's 4:20 right now, but I'm actually going to be making a CAD model just for this board, so I can mount it. So that's going to be something that we're going to be talking about, how to actually use tolerances to make sure that whatever you're making in 3D modeling fits whatever you're doing electronically. Because I understand a lot of, almost all of us on this team are electrical engineering majors. So it's important to see how we can use electronics and combine them with computer aided design to make a fully fledged and working model. Because in the end, we're actually going to have to integrate these holes and integrate these mechanisms into our electronics design. We're not just going to have like a PCB lying about. And so, this standard is actually really useful for that. All right, so go ahead and doing a full circle here and to these 2 edges too. And so while I'm doing this, does anyone have any questions to anything we talked about so far? Any questions, concerns? Am I going too fast? I know I'm going too fast, but any questions so far? All right. Well, if you guys ever have any questions about any of this stuff, you can always go ahead and message me on Discord or message in the server, and I'll be more than happy to help you answer. So what I'm doing right now is I'm making the arcs. So I'm making the curved edges of the PCB. And usually this, this is just another thing to make it look nice. The PCB fabrication companies will hate you for it because this is actually really hard to make. It requires more machine tools and machine stuff. But the thing about this is it prevents you from like stabbing yourself with the PCB because the corners are pretty sharp. So I like doing this. So you make this figure, right? And then you delete the guiding arrows. These are what this was for actually. It was for guiding it. And then you delete the 4 lines that make the 4 corners so that you're just left with these arcs. Okay. Now, again, I'm going to go ahead and draw another circle that's in the center of this circle to make sure that there's enough space for the screw. So remember, the screw has a 100 mm radius when the head is screwed in. So in this case, we'll actually see the screw perfectly fit within the terminal block constraints. So what you do now is you actually go ahead and just trace the board. You fill in the gaps. So you put a line here, and then you put another line here, all the way across. You put another line here, and then you put a line here. Okay, something like that. Okay, and then you see you have a little bit of black sticking out here. If I go to the 3D view, you can see I traced this on the top layer, but I actually haven't cut it out. So the PCB manufacturers are not going to be able to understand that I want this board to be cut out in a curved shape. So what I do is I have to actually define the board cutout based on these lines right here. So I go ahead and highlight these lines right here and highlight this. I go to design, board shape, define board shape, and now it cuts it out. Okay, so if I go to my 3 here, now I can see that the edges are now curved. And this is probably one of the more advanced techniques you'll see. Okay, so now we go back to the 2D view, and I want to make sure that I have holes. Now, to cut out holes in Altium, it might be different than KiCad, but I'm not sure. Altium has a specified tools panel in which you can go ahead and convert the circle to a board cutout. And so when you convert to the board cutout, it'll actually make this shape here, in which you can see in the 3D view, you'll actually see that is a complete hole all the way through the board. Now, sometimes you may be obligated to add something like a pad to this hole just so that you can ground it, but that's not necessary. So I'm going to go ahead and do that for the rest of the circles. I'm going to convert it to a board cutout. Convert this to another board cutout. Convert to a board cutout. And convert this to a board cutout. Okay, so if we go to the 3D view, we can see that now all the components are on the board, and our board has been successfully cut out now. So now we can access the voltage input, we can access the 5-volt regulated and 3.3 volt regulated output here. And all of our other components are still on the board. Great. So now what do we do? What we can do now is I'm going to just drag this a little bit down because the spacing is messing with me a little bit. What we do now is we have our board successfully wired or successfully placed all the components. We've done the board cutout. We've done the board shape. Now we need to actually route everything together. So routing is an important subject to talk about because we're basically replacing the jumper wires on a breadboard with traces, or what we call where it's actually copper. So what the PCB manufacturers do when they make these traces on your PCB is they pour a little bit of copper in between each wire, and in order to like show to the manufacturers that we need this, we're going to go ahead and press Control W, and we're going to draw a wire and replace the lines with whatever the wire is. And this is our route. So this is basically going to be copper. If we go to Control 3 to see this, it's going to be a little copper line between our terminal block connector and this capacitor, which is cool. That's all we want, right? Basically, instead of having to connect a jumper wire on a breadboard, now we have this copper infused wire inside of our PCB. Usually PCBs are made out of like FR4 or some kind of fiberglass material. So it's really cool to see. Now, here's an issue. This copper wire, it has a thickness of 10 mils. Now, this is really important, right? What we're building here is a voltage regulator. Now, presumably, this AMS 117 is going to allow up to 1 amp of current to pass through it. If we pass 1 amp of current through this small, tiny wire, what do you think is going to happen?
It's going to burn.
I'm using this to stall for time because I'm going to look for this. But passing 1 amp of current through that tiny little wire actually will cause it to catch on fire. And I've seen a video on YouTube before where this is true. Oh, shoot. Is my sound not working? Hold on. Oh no, my sound's not working. Oh, I didn't hear your answer. Sorry about that.
Yeah, I said the same thing you
I
said.
saw your mic on mute. All right, all right.
Can
I
you hear
have
me
sound
now?
again. Yep, I saw.
Yeah.
What did you say?
Yeah, I said the same thing you said.
Oh yeah, so
That's gonna burn.
goes kaboom. All
Yeah.
right, let me go ahead and play some background music so my headphones don't go out again. All right. But yeah, if you go online and search some videos of this stuff happening, you can actually see the traces, the thickness of the traces will determine whether or not your device will catch on fire or not. For 1 amp, I would say the safe amount, safe thickness is about 25 mils. So how do you change that? Now, when I did this for the first time, I spent like almost an hour and a half searching for how to change this. But in Altium, all you got to do is you got to go to design, got to go to rules, and you got to go to what's called, here, let's see. It's clearance, I think. No, not clearance. Routing width. Okay, so you go to routing width, and then you set the max width to 25 mils. Now you can go even bigger. If you have a max width of about 100 mils, that'll take care of like up to 5 amps, 10 amps, right? If you're passing like a current load through ACS 712, that takes about 30 amps, but you're going to need a really high load. So in this case, if I go ahead and do Control W again, now this time, if I go ahead and press W, I believe, oops, Control W, just kidding, Control Shift W, there we go. If I go to Control Shift W, now I can see that my trace looks a lot thicker than before, which is great. Now I can go ahead and route everything together like this. So if I go ahead and do a little bit of this action here, right? I just connect the dots, and it's pretty simple. Yeah, connecting the dots like here. Okay, so now you'll notice, you might be asking, why are my traces like this? Why are they at diagonal lines? Now, this is something that someone during my stream has talked to me about, but most people will say that you need diagonal lines in your PCBs just in case, because right angles are not good. If you have like really high current or a very high frequency signal going through your PCB, and you have a right angle turn, like really high frequency, like 1 megahertz or 1 gigahertz, right? The PCB is not going to like that. Usually in computers, you can see diagonal traces because that compensates for like the turns, like the electrons will turn through those angles and not through a right angle turn because it's too sudden. However, because I'm just using a DC signal here, I don't actually need to have, like 45-degree angles. It's kind of like the Mandela effect for PCB design. But it just makes it look a little bit nicer. So depending on how you PCB design, it's generally okay to do like right angle turns or something like that. But that's just the story behind it and how it got controversial over the time. For the AS117, again, I'm going to connect the 2-pin to the 4-pin to connect it together. And I'm just going to go around connecting all of these things together now. Okay, and you'll notice how I'm ignoring the ground pins. And that's because I'm ignoring the ground pins because I'm going to do a polygon pour on it later. I can get this to cooperate with me. So I'm going to do a polygon pour on it later, in which I'll cover the entire front face of the PCB with copper, such that all the ground connections will be connected together. Same with this one. I'm going to go ahead and connect this 3v3 outs to over here, this pad. Here, connect this pad here, and connect this 5-volt outs line to this line. I think that will work. I want to try to get it centered onto the pad because it looks better that way. There we go. Okay. I'll keep going from the 3v3 outputs. Oh, come on. It doesn't like it. I think my traces are too thick, or my spacing is too bad. Okay, something like that, and then finally 3 out to the terminal block. Okay, so I have nice thick traces here, which is great because if I have 1 amp of current, my PCB won't catch on fire. Now, the only thing I have to connect is the ground pin. Now, the ground pin is pretty easy to connect. All we need to do is add a polygon pore onto the top surface. You'll also notice that this PCB has 2 layers, a top layer and a bottom layer, but I did not connect the bottom layer because I don't need to, right? This is a simple enough PCB in which we can only need the traces on 1 layer. So again, a polygon pore is just a layer of copper that surrounds the entire top surface. If I change it back to 50, that surrounds the entire top surface. And you can make it go to some different pins on the top surface. So like if I go ahead and say, I want this to go to ground, I'm going to re-pour, then you'll see that suddenly all the ground connections are connected to the polygon pore. This spreads across the entire surface, and the ground connections are connected this way, right? So I don't need to wire the ground up because of this phenomenon. Same for this ground, same for this ground, same for this ground, same for every ground. So now we have a basic voltage regulator circuit wired up. And you'll see how that my polygon pore actually wraps around the corners, my weirdly shaped corner, automatically for me because I have this one rule in check. So if I have my board outline clearance, actually I don't have that, but like I kind of need it in order to make sure that my polygon pore doesn't reach outside of it. And if I go ahead and put a bottom layer, usually the bottom layer, you can either have a polygon pore net of VCC or just nothing at all. But in this case, I'm going to just put it there just to be safe. So a lot of times what people will do, and people will design a PCB, is they will put a polygon pore of VCC on one side and of ground on the other side. And this basically just makes a big capacitor on the entire PCB, and this smooths out all the connections. So it's really nice that way. So I have a top layer and I have a bottom layer, and we can see that both of them are connected. So now all I need to do is I need to resize all the text, and I need to upload this onto a Gerber file and get this produced. So I have a standard that I use myself to label all of these things. So if you see an Arduino, I have all these text. This size is actually standardized by me. Same for the Linky Learner. So everything, the hard part right now is just making sure that all text lines up because this looks a little bit ugly, right? So I'm going to go ahead and change all the text right now, really quickly. Let's say this VN is fine. And I'm going to set my text height actually to 40 and 6. I believe that is the standard I use for this. It's 40 and 6 and 25 and 6. So using the 25 mil, I can go ahead and neatly place my VN on top here. For capacitors, actually, capacitors are really small shapes. So my standard is 15 mil and 4 mil. Not 4 mil, 6 mil, maybe. But my value is going to be 10 microfarad. And this is where you can go ahead and put your actual label on. It is 4 mil. Okay, so 15 and 4. So this is where you can actually put your put this capacitor value on as a value of it. Alternatively, which I think I actually like this method better, is you can actually say the value and you can just go ahead and make it invisible. Now you can make it invisible like this, just by turning it off and clicking the eyeball. And the reason you do this is because you can put custom text. And every time you change the schematic from the other, every time you change the PCB from the schematic, you won't have to re-update this again. And I made the mistake the first time. So instead of doing that, all you got to do is I'm gonna go ahead and go to another PCB of mine. I'm gonna actually copy this text. Right, that's just a value, so that's not good. But something like let's see, one of my PCBs has it, not this one. I'm just going to copy this ground text here. Okay, and I go to PCB vreg, and then I'm going to go ahead and rotate this here. This ground is a text height of 25, so I'm going to change it to 15 and 4. Now you gotta be careful when changing the text type because if it becomes too small, then whoever's trying to manufacture your PCB won't actually be able to do it. So you got to check with your provider. Like mine is going to be JLC PCB to see if they're actually okay with doing this. So 0.1, 10 microfarad, something like that. I'll resize the text box. There we go. And I'm going to plop it in the middle here. Actually, it doesn't want to go to the middle. Come on. There you go. So I'm going to go ahead and copy this a bunch of times. There. Put there. Put there. There. Put there. Okay. So I have 10 microfarad and I have 0.1 microfarad, I believe. So 0.1 microfarad. And it's going to complain to me that my spacing is off, but usually it's okay. You can just like kind of ignore that. 0.1 microfarad. 1 microfarad. Oh, this is 10. So 10 microfarad. All right, so just checking with my schematic to make sure this is correct. 10.1, 10.1, 10.1. And then here I have 10.1, 10.1, 10.1. Okay, it looks good. And then I'm going to change this. Again, I'm going to make this invisible. So actually, I can actually change this to like 25 and 6 here, and then rotate it 90 degrees. It doesn't like rotating 90 degrees. So if I go ahead and rotate this 90 degrees, plop it in here, like that, and that centers itself automatically. Okay, again, change it to 25 and 6. Rotate it 90 degrees using the space key. Again, I have to change this to 3v3 now. That's a little bit too large. It's still a little bit too large, so let's say 3.3. Yeah, that's fine. Or I can just change the entire thing to 3.3 volts. Yeah, that's better. Okay, I'm gonna do this thing here. So 5-volt reg. All right, and then I'm gonna change this to 5 volts, and then 46. Okay, move it down here. I believe I had the spacing at 25 when I did that up there. Maybe like right here. Okay. Make it a little bit closer. This top layer, by the way, the yellow layer is called the silk screen. The silk screen, in a general PCB, you see all layers I have down here. There are a lot of different steps to make a PCB. And a lot of different steps entails like a lot of different layers. So and the top layer is usually called the silk screen on both sides. So you have the top silk screen and the bottom silk screen, and then you have your top layer, and then you have some other mechanical layers like invias, and then you have the bottom layer, and then you have the bottom silk screen. So if you want a more detailed in-depth look at that, you can probably go ahead and Google it. I know JLC PCB offers like a in-company PC manufacturing facility that you can like go ahead and tour around. Like it's actually impressive how JLC PCB manages to keep everything so cheap and affordable. Like 10 PCBs is like almost like just $2, but you know the shipping is insane. Okay, so now we have a completed PCB schematic. Let me just go ahead and put this label here. I haven't labeled my LED and resistor yet. say this is a 25.6. And this is going to be a 330 ohm. Like that. And then I'm going to say the same thing for here. This is an LED. That. All right. So now I have properly labeled all my components on this PCB. And if I go ahead and take a look at the 3D view, I see that everything is properly labeled. I have my terminal blocks here, some capacitors, the AMS chip, some more capacitors, an LED to indicate that it's going through, some more capacitors, all of them is routed. And you can just verify that it's all routed by, it's not going to complain at you and that there is any wiring issues. So that's all fine. I think I'm going to go ahead and put some more improvements on here. Namely, I'm going to put some text to indicate that if you're ordering from JLC PCB specifically, you actually need this tag somewhere on your PCB to indicate where they want to put the production number. Because JLC PCB requires that all PCBs have a number on it to specify, just for like their own logistic sides of things. And you can put this anywhere. I'll just put this on the back side. If you press L, it flips it to the back side, just so it doesn't disturb everything. Then, okay, and I'm going to put title to our PCB that we've designed. So let's say copy this text here. Paste this. And I'm going to say Banshee UAV Robotics volt linear voltage regulator. And I'll just yeah, that's fine. And just visually inspect it to see that it's even on both sides. You can actually add images and other fun stuff to your PCB if that's you're into that thing. And I can go over how to do that in a second here. Because sometimes it works great, sometimes it fails horribly, just depending on how well your SVG file is constructed. 760, okay, I was way off. Maybe like that. I always like trying to center things on the PCB, because you're spending a lot of money to make this sort of thing. Why not just make it look nice? 710, still way off. $640. By the way, I just checked the shipping on JLC PCB. It's close enough. Yeah, it's like $23 for shipping. It's ridiculous. Okay, so now we're done with creating our PCB. Theoretically, this should work, and it also has the mounting holes and everything. So it solves our black box problem of having a voltage input going through from one side, having an access point for 5 volts and an access point for 3.3 volts. And also we can actually mount this on some place, like a wall or something, using M2.5 by 6 millimeter screws. So what do we do next? Well, we want to give this to JLC PCB so that they can produce it. So all we need to do is, we already have the PCB, so we need to generate a Gerber file. And Gerber files are what the JLC PCB or fabrication companies use to manufacture the PCB. So in order to do this, you just go to File, go to Fabrication Outputs, and you go to Gerber files. Now, JLC PCB has their own little funny way of wanting you to produce Gerber files. So I'm going to go ahead and search that, and we can take a look. JLC PCB file tutorial. How to generate the Gerber files. Okay. So depending on what software you use, JLC PCB provides a guide on how to generate the file. So here in LTM PCB, you go to fabrication outputs Gerber files, and then they have some like weirdly specific settings that they make you do. I'm actually not sure if like these actually matter, but they want inches, 2.5 millimeters. The layers, I'm only going to say plot all used on layers because not all the layers are necessary. Some of them I didn't even use, like the mechanical layers. Drill drawings I don't really need. Aperture settings, they want to make sure you embed the apertures. And advanced settings, you need to check because this is where like a lot of stuff gets messed up. They want you to use the software arcs, and everything else should be okay. Okay, so then the program is to work generating the Gerber files. You get to see a really nice view, the Camtastic Cam view, which I don't really use unless you're actually making this PCB on kind of like a on a CNC mill, which I actually have. You can actually make your own PCBs, and you don't have to send it to a fabrication company and wait 2 weeks. But you know that takes a little bit more skill and more experience of working with this stuff. Okay, so you generated your Gerber files. If you go to the left tab, you can see in the generated folder, you can see your Camtastic documents and also some text documents. These Camtastic documents are the Gerber files, so you need all of these. So in order to order on JLC PCB, you'll need to go ahead and zip this all up, drag it into their Gerber viewer, and let them check it for you. So JLC PCB has some very nice customer service. They can't speak English very well, but they'll check it for you and make sure that you have all your layers and all the things that you need. So in addition to the Gerber files, JLC PCB also requires something called an NC drill file. Now, this is for them to know where to drill into the PCB. So like the holes I have here, they need to know where to drill that in. The holes I have in the through hole components, like the VN port or the 5-volt terminal block, they need to know where to drill that in. So all I need to do is go to fabrication outputs again, and I think it's NC drill files right here. And JLC PCB wants inches with 4 significant figures this time around. I want to suppress leading zeros, reference to relative origin, and optimize change location commands. So after I do this, it'll open a Camtastic drawing of just where everything is drilled. Now, the fun thing about this board is that I made everything using SMD components, which means that the only thing that gets drilled in is the terminal blocks right here. It's the left, up, and the right part, which is great because save, drill, make our holes look nicer. There is also the board size drill hole, but they don't count that in because that's already part of the board shape process. So they only drill this in while they're making all the other paths. I'm gonna not save that. Great. So basically, we've designed our PCB now. Now I'm gonna go ahead and show you guys what it looks like on actually JLC PCB. I'm gonna log into my account and show you because I think it looks pretty interesting. So I'm gonna go ahead and go to JLC PCB. JLC PCB. Now, JLC PCB also has their own part repository. In case you want some SMD components, you can. You can just buy them straight from JLC PCB. And by the way, they're a lot cheaper than Mouser Electronics or DigiKey sometimes. But you also got to buy like 1,000 of them at once, and sometimes like that's not something that I want to have. I don't want to have just like 1,000 surface mount resistors just sitting next to me, even though I do have that. Okay. So when you guys design the power team, especially when you guys design the PCB for your circuit, we'll order them all at once using the Banshee account. And like, oh, like look at this. Shipping $21.56. That's ridiculous. it increases by weight too. So the more PCBs you order, the more expensive that's going to be. $21.56 is just the base cost. I remember for one of my orders, I'll show you guys. When I ordered, here's all of my files. Order history. When I ordered the Blinky Learner PCBs, the merchandise total was $55, but the shipping charge was $41. So it cost them $50 to just, I paid for this plane ticket to send this package to my house. And this was the circuit I used for Blinky Learner here. Same for this one. For my Sound Voltex boards, for macro boards, the shipping charge was $83 for 100 boards. And like, so a lot of times, actually, like for this prototype batch, the shipping charge is usually more expensive than the actual merchandise cost. So some like ride sharing stuff needs to happen. if you're like trying to buy a bunch of PCBs with a friend, because shipping is just expensive. You kind of want to try to minimize on that if you can. Okay, so I'm going to go ahead and try to order this PCB that we just designed here in this workshop. So if I go to projects and go to Banshee demo, I can actually see, if I go to project outputs, all of this here is my Gerber file. So if I go to send to the compressed Z file, I'm going to rename this to Banshee PCB vreg, like this. If I drag this zip file into a JLC PCB and it processes it for me, I can actually see the Gerber file and how it looks like. So it says it detects a 2-layer board of this size, and wow, my special price, I can have, how many boards is this? It's 5 boards. I can have 10 boards for $5, which is a great deal. Or I can have 5 boards for $2, which is also a great deal, right? And we can see that our board looks like exactly how we designed it. We have a PCB here, in which we have all our components on there. And everything looks pretty nice. We can also have PCB assembly, so we can have them assemble it for us. But we need to confirm like where all the parts are. And I don't want to do that right now. So when it gets to time to ordering all the PCBs, especially for the power circuits, we'll just do them all in one order, one big order. So eventually we'll see this thing in person, hopefully by the end of the summer, but not as of right now. So this is actually what it looks like. Big long strip of PCB, and this is one whole circuit. So again, we have inputs as the terminal blocks and the outputs as 5 volts and 3v3, which solves our problem statements. All right. Okay, so I know I went way over time. It's 4:50 right now. But does anyone have any questions on just general PCB design and how to make your own circuit inside of Altium or KiCad? I have my sound on this time. Okay. If no one has anything, if you guys are watching the recording afterwards, you can feel free to message me if you have any questions. But that's going to be all for this workshop. In a few minutes after this intermission, I'm going to start off the CAD workshop in which I'll be making a case for this. So in case you want to, mount this on something, you can. So it's going to be a follow-up to this workshop. So in case you want to see something cool or something cool CADed up, I'm just going to wing it there too. To mount this on, we're going to be talking about screws, tolerances, how to like do stuff like mounting 9-volt batteries and stuff like that, how to get a VN import, and how to just in general mount this really well. So how to export it out of Altium as an STL and import it into Fusion 360 as a CAD file. Okay, so that's all for this workshop. Thank you guys for watching. If you are looking at the recording, I hope to see you in the next workshop for those of you who are on Zoom. And I wish you a great rest of your day. So bye for now.